Greetings! We are from Dnipro, enthusiasts and lovers of space exploration. We enjoy solving tasks in both technical and astrophysical aspects to advance humanity into interstellar space. Our team is named INTERSTELLAR, which means interstellar. I am Mikhailo Simonenko. Since I was 6, I've been fascinated by space and have profound knowledge in astronomy. I have extensive experience in practical astronomy and study aerospace engineering at the physics and technology faculty. Valadian Mars Teksenko, Sergei Kaznov, Botan Bokan, and Habitat Exlananis, creating worlds beyond our own. Our task is to use publicly available information about exoplanets to design our own world and write about what life could be like on exoplanets. Today, we know of 5,523 confirmed exoplanets. We focused on the exoplanet Kepler 452b in the constellation Cygnus. Per hour, it's 1,800 light years away. Its star belongs to the yellow dwarf class, just like our sun, with almost the same surface temperature, but it's brighter due to its larger. This star is 1.5 billion years older than the sun. There's been plenty of time for life to develop. A full orbit around the star takes 19.8 days longer than an Earth year. The exoplanet is in the same habitable zone as our Earth. In size, the exoplanet is 1.5 times larger than Earth, and its mass is 29 times greater, classifying it as a super Earth. This allows it to retain more atmosphere and light gases such as hydrogen and helium. The pressure and density of the atmosphere will be higher. Depending on its composition, such an atmosphere could protect life from ultraviolet radiation even better than Earth's atmosphere. The planet's metallicity is the same as Earth, so there's protection from cosmic radiation, a magnetic field. The Earth similarity index is 0.83, corresponding to rocky Earth-like planets that might have an Earth-like atmosphere with moderate temperature and support terrestrial life. The equilibrium temperature on the exoplanet without an atmosphere averages 8 degrees Celsius, while on Earth it averages 18 degrees without an atmosphere. Through the atmosphere and the greenhouse effect, the average temperature on Earth is 15 degrees Celsius. If the composition of an exoplanet's atmosphere is similar to Earth's, the average temperature would be 1 degree Celsius. Using these characteristics, we modeled the appearance of the exoplanet as if there were life on it. You see that the majority of life is found in water rather than on land. Life has primitive and simple forms that are just emerging from the water onto the land's surface. Near the water, you see blue moss. This blue moss dominates on land, and there is much more of it than due to gravity, which is twice that of Earth's. The terrain and mountains are much lower, and the oceans are smaller than those on Earth, increasing the size of warm water zones favorable for life. But why is the moss blue and not green? It's all thanks to the chlorophyll, which determines the color. Chlorophyll facilitates photosynthesis, the conversion of light energy into chemical energy. During photosynthesis, chlorophyll absorbs light energy to produce organic compounds and release oxygen from carbon dioxide in the water. The amount of light energy absorbed by chlorophyll depends on many factors, including light intensity and the spectral composition of the light. However, chlorophyll only absorbs certain wavelength ranges. To produce Earth's oxygen, it absorbs blue and red wavelengths from the spectrum, reflecting green. Hence, Earth's plants are green. Emission of blue and red colors have different wavelengths, thus differing in light photon energy. Red has longer waves, while blue has shorter ones. Due to the shorter wavelengths, blue color carries more energy than red. As a result of evolution in Earth's conditions, our plants absorb parts of the spectrum that are necessary and balanced to get a certain dose of energy from the sun. On exoplanets, where the illumination from the star differs in both intensity and spectral composition, the absorption spectrum of chlorophyll would likely be different. If the star of an exoplanet is brighter than the sun, it is expected that plants will absorb the red and green zones of the spectrum, reflecting the more energetic blue. Thus, they would have a blue or cyan color, as opposed to Earth's green plants. However, if the star were dimmer, the color would be different, such as with the exoplanet TRAPPIST-1e. Its star is a red dwarf with an V-class spectrum. The star is dim and emits more infrared radiation than in the visible range. It emits ultraviolet light 6 times less than our sun. The energy from the star reaching the exoplanet is 35 less than what Earth receives. Under such conditions, vegetation is considerably darker because chlorophyll will absorb the entire spectrum of radiation: blue, green, and red. There may be a slight reflection of red rays. As a result, planets are either entirely black or dark red. TRAPPIST-1e is the 4th exoplanet out of the 7 discovered. It is almost the size of Earth, but slightly smaller, and its mass is 30 less. In terms of habitability class, it is classified as a mesoplanet, considering the approximate equal distances of Earth and TRAPPIST-1e from their respective stars in the habitable zone. We conclude that the processes of life formation might be roughly similar. We have modeled the appearance of this exoplanet. Due to tidal locking, synchronous rotation of the exoplanet is possible, where one side of the planet always faces its star, similar to how the moon faces Earth. One side is scorching and inhospitable, while the other side is perpetually in the shadow and eternally cold. Only a band along the border between light and shadow is conducive to life. There will be a significant temperature difference between the sunlit and shadowed sides, which, in the presence of a dense atmosphere, will result in constant hurricane-like winds. The wind will blow from the cold side to the hot side near the planet's surface. At higher altitudes, the wind direction will differ and depend on a multitude of random factors. In the life-suitable zone, a significant portion of liquid water will accumulate, raining down from clouds formed on the hot side. Glaciers from the dark side will periodically melt and freeze in the border zone, providing the crucial water for life's development and ensuring its cyclical circulation. To survive the sharp temperature fluctuations, organisms in the water will migrate following the zone of comfortable temperature, for example, from the sunny edge to the shadowed side and back. On land, red moss predominates. In the light of a dim star, the landscape will have a reddish hue. Overall, the planet experiences a twilight-like atmosphere. The star mainly neither sets nor rises beyond the horizon, but as the mechanics of planetary motion show, there will not be a perfectly static position of the star in the sky. Just as with our moon, there can be libration on this planet, a slow oscillation of position and a slight rotation of the star relative to the observer. It looks the same as we observe the moon from Earth. Thus, the star will slightly rise and fall relative to the horizon in some zones due to libration. A day-night cycle is observed. The cyclical nature of life might adapt depending on these librations. If the libration periodicity is very long, seasonal changes can occur. However, this differs from Earth, where it happens due to our planet's axial tilt relative to the plane of its orbit. In conclusion, it's essential to know the composition of an exoplanet's atmosphere for modeling. The James Webb Telescope, using the NIRISS and NIRSPEC spectrometers, conducted an analysis of the exoplanet K2-18's atmosphere. It showed the presence of carbon dioxide, methane, and dimethyl sulfide. This is a remarkable discovery and crucial information, as dimethyl sulfide is produced only by living organisms, which produce it during metabolism, for instance, phytoplankton and microalgae. However, one should not jump to conclusions, since the information about the presence of dimethyl sulfide in the exoplanet's atmosphere is preliminary and requires further confirmation. It's entirely possible that there's some natural process synthesizing it without the participation of living beings. Typically, in nature, dimethyl sulfide is a biological organic sulfur compound released into the atmosphere. It's colorless, mobile, flammable, and volatile, with a sharp, unpleasant smell reminiscent of sea air. Methane rarely remains in the atmosphere. If it lacks continuous sources, its concentration drops to 0. It's easily destroyed by the star's light. If its concentration remains significant, there's a methane source on the planet. Typically, methane sources live in water. It's logical to assume there's an ocean. In 2019, 2 independent scientific studies combining data from the Kepler, Spitzer, and Hubble Space Telescopes concluded that exoplanet K2-18 has a helium-hydrogen atmosphere with a high concentration of water vapor sufficient to form clouds. In terms of its mass, it is classified as a super-Earth. The exceedingly low average density of 2.4 grams per cubic centimeter suggests that this planet is likely a mini Neptune. However, spectroscopic data infer that the planet might be a water world consisting of a single ocean. Given all the aforementioned information, we have modeled how the atmosphere would look based on James Webb's graph and additional data from Kepler, Spitzer, and Hubble. Methane in the atmosphere can interact with the star's radiation and create additional optical effects, enhancing the scattering of light with shorter wavelengths, contributing to the appearance of red and pink hues at sunset. And the presence of aerosols from carbon dioxide might also lead to the emergence of pink and purple sky tints at sunset, complementing the effect provided by methane. The exoplanet doesn't always orbit within the habitable zone. Sometimes it exits this zone and enters a hotter region, creating steam clouds that envelope it like Venus. Then it returns to the habitable zone where heat and mass transfer processes normalize. If subsequent analyses confirm the presence of dimethyl sulfide, there could be Phaeocystis on the ocean's surface. This common marine phytoplankton can function in a broad temperature range, tolerating both intense heat and cold. The high productivity of Phaeocystis typically lasts for about a 3-month period. Representatives of this genus dwell in the open ocean, on the surface, in the water, and even within ice. It has a polymorphic life cycle from free-living cells to large colonies, forming a fragrant foam on beaches during bloom decay. Their ability to create vast areas of white foam on the surface and widespread proliferation makes Phaeocystis an essential participant in the ocean's carbon cycle. Moreover, Phaeocystis produces more dimethyl sulfide than other representatives and plays a global role in the biogeochemical sulfur cycles, which can influence cloud formation in the atmosphere and potentially regulate the climate. It also forms a crucial part of the marine ecosystem and influences planetary processes. We modeled how this looks on the exoplanet using neural networks. On the surface, you see white foam from Phaeocystis, a semi-transparent mist with massive clouds. As a result, on a planet with an atmosphere of methane and carbon dioxide, at sunset, you'll witness warm and saturated shades of pink and red, creating a beautiful and atmospheric spectacle. Thank you for your attention.